Hey students, we're going to go over acid-base equilibrium. So in one of the previous videos, I talked about how the concentration of a strong acid or the concentration of a strong base could be used to find the concentration of your hydrogen ions in the cases of acids or the hydroxide ion in the cases of base. And that's because with strong acids and strong bases, those dissociate completely into their ions. But as we discussed, weak acids and weak bases do not dissociate completely. So that means there's still going to be some whole acid molecules found in the solution and some hydrogen ions and some anions in the case of a weak acid. So in those cases, with weak acids and weak bases, we have to solve the problems the same way we did in the equilibrium unit and use Rice tables and Ka and Kb values. So when we're going to write these expressions, we're going to use the same kind of idea as we did for the equilibrium unit. And it was, if you remember, products over reactions. Now, our values here, our Ka values, because it's going to be products over reactants, we're going to have a concentration of hydrogen ions times the concentration of, this represents just a generic anion, because this is just a general acid formula here with an H in front. And we're going to put that over the concentration of our acid molecule. Okay? So for this one, we've got a specific acid, cyanic acid, HCN. So our Ka, the A stands for acid, K is our equilibrium constant, is going to be the concentration of H plus times the concentration of Cn minus over the concentration of HCN, okay? Now, as a note here, it says that the larger the Ka value, the stronger the acid. We don't have to do these for strong acids because they dissociate completely. There is no more Ha left, okay? So the closer it is to 1, the more that it has dissociated. So that's why the larger the Ka value, the stronger the acid. Same goes for bases. And this is what I was just talking about. We don't have Ka values for our strong acids. We don't have Kb values for our strong bases because they have dissociated completely. There is no acid left. There's no base left. Now, when we have a diprotic or a triprotic acid, meaning that there's more than one hydrogen in that acid, each hydrogen ionizes individually. So it only ionizes one hydrogen at a time. So that means each hydrogen would have a separate Ka value. So in this case, for carbonic acid down here, H2CO3, you can see that there's going to be one Ka value for the first hydrogen that dissociates, and then a second Ka value for the second hydrogen that dissociates. So it's going to be the same thing for our weak bases. Now notice that this reaction looks a little bit different than the acid one does. The acid, if you remember, it was Ha, is going to dissociate to make H plus ions and an anion. With bases, it's a little bit harder to see because you could have something like this where there's not a hydroxide in the formula. So it's hard to envision why there's a hydroxide that pops up on the product side. So what we recommend you do for bases is to write water in that reaction, because remember, this is dissociating in water. That way you can see that one of these hydrogens, one of these hydrogens from water comes over to the base, because as we know, bases accept hydrogen. That's why we end up with a hydroxide ion over here. But remember, when you write a Kb value, because it's the concentration of your products over the concentration of your reactants, the water, because it is a pure liquid, does not show up in that equilibrium expression. So it's still the concentration of your ions over the concentration of your base. And again, the larger the Kb value, the stronger that base is. So when we work out our Ka and our Kb problems, we're going to do this the same way and set these up the same way we did in our equilibrium unit. So we have to write out our reaction first. We need to see what ions it's going to dissociate into. We're going to set up our Rice table. Yes, we must have a rice table for weak acids and weak bases. We're going to write out our Ka or our Kb expression without any numbers first. We don't want to take any shortcuts because that's where we make some mistakes. We'll solve for our Ka or our Kb for X. Now, X is going to represent our ion concentration. You'll see that in just a second. So if it's asking you for the pH of a weak acid or a weak base, you have to keep in mind that the X is your ion concentration. So then you'll have to solve for the pH from that ion concentration. But we'll go over those examples so you can see exactly what I mean. So let's look at example 28 here. I'm going to make this a little bit thicker on my writing utensil. It says calculate the pH of a 0.10 molar solution of acetic acid. The Ka for acetic acid is 1.8 times 10 to the negative 5. So first off, we write our rice table. This is a Ka problem, so that means we need to have a rice table. Now, acetic acid is going to be HC2H3O2. And it's going to dissociate into a hydrogen ion because acids provide a hydrogen. And then what's left? C2H3O2, negative. So it says that we have a 0.1 molar solution of acetic acid. So that is our initial concentration of acetic acid. As with equilibrium problems, we start with no products. Now remember, we are losing some concentration on our reactants and we are gaining some concentration in our products. So our equilibrium row is going to be the I and the C put together. We will write our Ka expression without any numbers. So remember, it's going to be the concentration of our products over the concentration of our reactants. So then we'll put HC2H3O2 down here. So now that we have our equilibrium expression without numbers, we can go ahead and plug our values into our equilibrium expression. So our constant is 1.8 times 10 to the negative 5th. We're going to have on the top x times x, so that's going to be x squared. And on the bottom, we're going to have 0.10 minus x. So you can see that our x's are not raised to the same power in our expression. So that means that this x on the bottom is negligible. So we can make that negligible. We go ahead and multiply both sides by 0.1. So we have 1.8 times 10 to the negative 6 is equal to x squared. Once we get here, then we can square root both sides in order to get x by itself. So let's see what that value of x is. Whoopsie. Sorry. Square root of 1.8 times 10 to the negative 6. And my x is 0.0013 molar. Now, because when I look at my equilibrium expression, I see that my H plus is the same as X, so that X is giving me my hydrogen ion concentration. So if it was asking me for hydrogen ion concentration, I could stop there. But it's asking me for pH. So how do I solve for pH given my hydrogen ion concentration? Well, I would simply do a negative log of my hydrogen ion concentration to get my pH. So I'm going to do negative log of my answer, and I get 2 sig figs, and those go behind my decimal point, so my answer would be 2.87. That would be my pH. Okay? Next example, calculate the pH of a 0.25 molar solution of HCN. The Ka for HCN is 6.2 times 10 to the negative 10. Now here is a handy dandy little trick. If a question is mentioning the Ka value, you're going to need a rice table. Okay? So you don't even have to think about it. I need a rice table. So I've got HCN. Now remember, this is going to dissociate into ions. So that means it's always going to make an H plus because it's an acid. and then whatever is left is your anion. I've got a 0.25 molar solution of this, and I start with none of my ions. Then remember, I'm going to lose some concentration on my reactants, and I'm going to add some on my product side. So then that means for my equilibrium row, I've got 0.25 minus X, and then X and X over here. So I'm going to write my equilibrium expression without any numbers. I've got my products on the top, and I have my reactants on the bottom, HCN on the bottom. So I can go ahead and plug everything in. So my Ka was given to me in the problem, 6.2 times 10 to the negative 10. I'm going to plug in my equilibrium row into my equilibrium expression. So that means I have X times X on the top, X squared. I've got my equilibrium of HCN on the bottom, 0.25 minus X on the bottom. So it looks very similar to the last one. They're all going to look really similar. Now, because my X's are not raised to the same power, that means my X is negligible. So I can go ahead and multiply 6.2 times 10 to the negative 10 by 0.25. And I would get 1.55, I'll do sig figs at the end, 1.55 times 10 to the negative 10 equals X squared. So then I got to get X by itself, so I shall square root both of these. So then square root of that answer is going to be 1.2 times 10 to the negative 5th. Now it's asking us to solve for the pH, and X is representing my hydrogen ion concentration. So that's my hydrogen ion concentration. So when I go to solve for my pH, all I have to do is do a negative log of that answer, 1.2 times 10 to the negative 5th, and that is going to give me my pH value. So negative log of second answer, 4.90. And that's it. The next thing that we'll talk about is how to determine the percent dissociation of a weak acid. So if it's asking you to solve for the percent dissociation, we would have the amount that's dissociated. So basically that's going to be our X over our initial concentration. So you can see that's going to be your final hydrogen ion concentration divided by your initial acid concentration times 100. So for that last problem, this was our hydrogen ion concentration. So that's what we're putting on the top. This was our initial concentration, so that's what we would be putting on the bottom. And you can see it, we have 1.2 times 10 to the negative 5th divided by 0.25 times 100. But let's walk through a whole problem to see how this works. So calculate the percent ionization of a 1.75 molar solution of chlorous acid. The Ka is 1.10 times 10 to the negative 2nd. So we're going to need a rice table. So we'll go ahead and write this out. Chlorous acid is HClO2. And when you write the ions, we have H plus, and then whatever's left, ClO2. Our initial concentration is 1.75 molar. We start with none of our ions, and then we always lose some reactants, and we add some products. So we have 1.75 minus X, X, and then X over here. The next thing, we are going to write our equilibrium expression without any numbers. So the Ka is going to be the concentration of H plus times the concentration of ClO2 minus over the concentration of our acid, HClO2. We can go ahead and plug in our numbers. So we have 1.10 times 10 to the negative 2 is going to equal X times X, so X squared on the top, over 1.75 minus X. And because the X's are not raised to the same power, our minus X is negligible. So we'll go ahead and multiply our Ka, 1.1 times 10 to the negative 2, by 1.75, and we get 0.01925 is equal to x squared. We're going to square root both sides of this so that we can get x by itself. So we will square root this. We'll get 0.139. Now remember, the x is equaling our hydrogen ion concentration. So that's our hydrogen ions. It wants us to solve for the percent ionization though. So what we're going to do to solve for our percent ionization, we take our concentration of the hydrogen, 0.139, and we divide it by our initial concentration, 1.75, times 100. And again, I always just use the unrounded values in my calculator when I'm doing all of this work. So if your answer varies slightly from mine, that's okay. So my percent ionization would be 7.93%. Okay, so that's how you do Ka and percent ionization. We'll go ahead and do the Kb in the next video, okay?